Hi Chem 1211. Let's do Chapter 7 right this time. We're going to start by talking about the electromagnetic radiation very quickly. Once again, light, which is what electromagnetic radiation is just our way of moving energy to and from things that are very, very small. I mean, we can move it to anything of any size, but we're going to be using it to look at atoms. So we want something small. Once again, it's made of an electric field and a magnetic field. When you study physics, you'll learn more about that. Light comes in a variety of types. We're used to the visible ones, but the description that we use to characterize the types is wavelength is one thing that we use. We also use frequency. So we've got wavelength, which is lambda, and we got frequency, and they're connected by this nice little thing right here. It's an equation, lambda times nu is equal to c. Lambda times nu is always equal to velocity for light, or for a wave, but for light it's equal to c, where c is the speed of light. It's a constant and will always be given to you. At the same time, if we know the frequency or the wavelength, we can calculate the energy, because the energy is equal to h times nu. H is another constant called Planck's constant. That all said and done, if we take any kind of light, we might have different types of light that we give names to, such as radio, microwave, infrared, visible, ultraviolet, X-ray, or gamma ray. We've given those names, but really there's numbers associated with them, and they represent the whole possible spectrum of light. First noticed by people who saw rainbows, and by Newton, who saw that we could do the same thing by using a prism, which is what we show here, or something like a grating. There are many devices that can separate light out into its components. The key thing is we can put numbers on light if we have to. I'm not expecting you to know much about this, except you should probably know that light that we see, the visible light, is in a wavelength of nanometers between 400 and 750. So if you know that, then you're in really good shape as this class goes on. The key thing is we know that there's different types of light, and they're different. They do different things to atoms and molecules when they interact with them. So let's have a pretend interaction right now. Let's send some light. So this is sending light in. Sending light towards some type of atom. I'm hoping you can recognize this atom right here. It's the same in all three experiments. What kind of atom is that? I hope you screamed out with one proton. That's a hydrogen atom. Yeah, it's a hydrogen atom. In the first experiment, if you notice, 3 photons in, 3 came out. In the second experiment, 3 photons in, only 1 came out. And in the third, 3 photons in, 3 photons out. Now let's investigate these energies, because if you look carefully, they're not very different. They change by roughly 4% each time. That's not a lot. So what's going on? Why is the atom so picky about what it absorbs? So that's a question that anyone who's going to try to model the atom, gives a picture of what it looks like, should be able to answer. At the same time, they should be able to answer this weird conundrum, and that is, if we have glass in front of our light, ultraviolet light can't get through. That's high energy. It cannot break through the glass. Yet visible light goes straight through. And oddly enough, infrared light also gets stopped right at the barrier. So this is another thing that was very confusing to people. How can it be so selective as to only let one type through and not the others? So that's when the Bohr atom was invented, soon after, and it actually explained this with the simple idea of, if an electron is on an orbital, then when it absorbs energy, it is promoted from one energy level to another. Depending on what energy level it's at, it would go from one energy level to another, and it has to land exactly on the new energy level for it to be stable, for it to stay there. So when we ignore the light, it's because it sends the electron somewhere in between, or somewhere short, not dead on the next orbital that it needed to go to. So that was the Bohr atom and how he figured it out. We'll pick up from there in our next 5-minute little video.